Hi, everyone. Thanks for attending my talk. I'm Daniel Gutierrez from the University of Sevilla. And today I'm going to present our work in collaboration with the group of Chiara Bartolozzi from the Italian Institute of Technology called towards the neuromorphic implementation of the auditory perception in the iCub robotic platform. So this is the outline of the presentations. I'm going to start giving our motivation, explaining why we started this project, and then I will briefly explain how the auditory ascending pathway, the biological point of view works. Then I will introduce the iCub robot, and then I will explain in detail, more or less, how we implemented the neuromorphic models for giving the iCub the hearing sense. Then, because this is still still a work in progress, I will show the preliminary results, and then I will discuss some improvements and future works that we have still to do. So, what's the main motivation of this work? When I started my PhD, I went to the Kapukashi neuromorphic workshop, and then I met the iCub robot there, and I really liked the robot. But the problem that I detected was that it had vision, it had touch, but it didn't have the hearing sense. So my biggest motivation, because my PhD is related to neuromorphic auditory sensor or perception, was to provide the iCub with the auditory sensor. And as far as we know, this is the first time a neuromorphic cochlear model is being implemented or integrated on the iCub robot. So I will briefly explain how the auditory ascending pathway works. So here you can see the big picture of the ascending auditory pathway, in which the first part we can find the cochlea. So the cochlea is located in the inner part of the ear. So we can't. The ear is divided in or split in three parts: external ear, in which we can find the auricle, the middle ear with the auditory canal, and then the inner ear with the cochlea. And how the cochlea works, or one of the most important part of the cochlea, is the basilar membrane. This membrane decomposes the sound, the input sound, in their main frequencies, and it works similar to the Fourier transform. So this basilar membrane is organized phonotopically, and that means that each part of the basilar membrane responds to different frequencies, starting in the base with the high frequency sounds or frequencies, and ending in the apex with the low frequencies. In humans, this range goes from 200 hertz until up to 22 kilohertz. When the basilar membrane is responding to the frequencies or the main frequencies of the input sound, it is exciting the inner ear cells that are producing the spikes or the events that then are sent through the auditory nerve. These output spikes are sent to the next nuclei, which is called a superior olivary complex. Here we can see that the superior olivary complex has four main nuclei: the cochlear nucleus, and then the medial superior olive and the lateral superior olive. Those two nuclei are responsible to extract the binaural cues to perform the sound source localization. These two binaural cues are the interaural time difference that measure the time difference that the sound waves arrive to the left and the right ear, and the interaural level difference measures the intensity or the level, the difference of the sound waves arriving to the one ear and to the other, because the head acts like an acoustic shadow. We also have the spectral cues to determine or localize the sound source in the vertical axis, because the binaural cues, the interaural time difference and level difference, are used to localize the sound source in the horizontal plane. For extracting the interaural time difference, the most accepted model is the Jeffreys model, that is based on an array of coincident detector neurons and also a set of delay lines. So when spikes arrive to the right and the left ear, the spikes are transmitted through these delay lines. And when a coincidence detector neuron receives a spike at the same time in a short time being, it fires on a spike, and depending on which neuron fire, we know where is the sound source. Similarly to the medial superior olive, the lateral superior olive is able to extract the level difference, and this is basically to compare the firing rate of the neurons. So the output firing rate of the neurons is kind of subtracting the firing rate of the neurons from the left ear and the right ear, and the output firing rate, we can kind of do a interpolation and then localize the sound source. These output spikes are sent to the inferior colliculus that combines these binaural cues and the spectral cues to have a final decision of the localization of the sound, and it also performs the first step of the involuntary auditory attention. Also, these output events or spikes from the inferior colliculus are sent to the superior colliculus, where we combine this information with all the sensory information coming from the vision and the touch for performing more and more complex tasks. Finally, this all information is sent to the auditory cortex to perform some sound recognition as learning. Also, in this part of the brain, we do the voluntary attention and well as tonotopically organized. So that means that we know which part of the brain has to react or have to have a response according to the input sound. Then I really would like to introduce iCub. So iCub is the humanoid robot that looks like a child and is developed by the Italian Institute of Technology. And the normal version of the iCub has two cameras as eyes, two microphones as ears, and also have skin and fingertips, as well as motors for moving the joints. But we also have in the group the neuromorphic version of iCub that is, instead of having normal cameras, it has two neuromorphic retinas, two ATs in the eyes, and also the skin is event-based. This neuromorphic version of iCub also have direct interface with the neuromorphic platforms from deploying spiking neural networks as Loihi and or Spinnaker. But still, as I said at the motivation, we have traditional sound processing system. So we wanted to include or to integrate a neuromorphic auditory system to have the fully neuromorphic iCub. For using the iCub, we had the JARP framework. That's a very nice framework, open source. That's based on C++ that interface the hardware devices with the robot, and then you can communicate the hardware devices and you can move the robot. It is fully modular. That means that when you want to include new functionalities, you just need to include or to create a new module and integrate your new module into the software. So the big question: how we are going to give to the iCub the sense of hearing? So the main contribution of this work is that we designed and implemented a digital version of the Jeffreys model to extract the intraoral time difference, and we integrated this new model with an existing model of the digital neuromorphic cochlea that was implemented by my supervisor that we call NAC, Neuromorphic Auditory Complex. After that, we integrated this new module for FPGA within the iCub robot, and we also add the needed software in JARP to support this new model. Furthermore, we collect data sets for analyzing the response of this new model on iCub. We implemented the first version of the inferior colliculus model using spiking neural networks on Spinnaker. And finally, we prepared an open loop simulation demonstrator for the sound source localization, moving the iCub heads towards the sound source. So, as I said, if we would take as reference this picture, including the cochlea and the nuclei needed for extracting the auditory cues, what we propose is to have both the cochlea and the superior olivary complex implemented as neuromorphic models, event-based models on FPGA, and the inferior colliculus and auditory cortex implemented as a spiking neural network on Spinnaker. So for implementing the cochlea, my supervisor implemented the neuromorphic auditory sensor, or NAS, which is a digital spike-based cochlea model with a cascade architecture based on the Lyon's cochlear model. The main difference between this cochlear model and other cochlear models is that we convert the input sounds directly into spikes at the beginning, and then we perform the sound decomposition in frequency bands already in the spikes domain. This has a big advantage. So if we don't have audio, that means we don't have spikes. Therefore, the processing filter bands are not working. It's not doing anything. Thus, we are saving some power consumption, which is the main point of the neuromorphic sensors. So for implementing this bandpass filter for the cochlea, we have a cascade of low-pass filters connected in cascade. So the bandpass filter is the result of subtracting two consecutive low-pass filters. Another advantage of this cochlear model is that it's fully open source, and you can generate your own cochlear model through using the OpenNAS tool that generate automatically the FPGA files that you can directly compile and generate or simulate the model. This is how the NAS response looks like for a 64 frequencies channel NAS when a person is saying en un lugar de la Mancha. So top plot is the raster plot of the events, and bottom plot is the sonogram, which is the energy of the output. So we used the PyNavis tool, which is an open source tool that we developed in our group to analyze the cochlear output. After that, the cochlear events are sent to the Jeffers model that we implemented for the FPGA, and for that, we implemented the coincidence detector neurons using the Hall-and-Fire coincidence neurons, and the delay lines, we used the Hall-and-Fire model. These two models are very simple because it can be implemented at a finite state machine. So for the coincidence detector neurons, we have an array of these models, and for the delay lines, we need two Hall-and-Fire neurons or models for each coincidence detector neuron. Basically, this finite state machine, what it does is when a spike is received, it holds the spike in a time being, and in the case of the delay lines, after a certain period of time, the spike is released, and for the Hall and coincident fire, it holds the spike for a time being, and if it detects that another spike is coming, then the spike is released, but if it doesn't detect any coincidence, the spike is deleted. And as you can see, the resources consumption is so slow that we can have many of these models in a single FPGA. So after that, to combine or to integrate these two models, we created the neuromorphic auditory complex that is basically to integrate the cochlear model, the NAS, and the superior olivary complex model. In this module, the input will be the microphone's output, and the output of the module will be the AER events coming from both the NAS and the superior olivary complex. So here in the top, you can see how the AER event format looks like, having 7 bits for the frequency channel of the NAS that allows us to have up to a cochlea with 128 frequency channels, and having 5 bits for identifying the neurons, allowing us to have up to 32 neurons per channel to extract the interaural time difference and interaural level difference. And to integrate this into the iCub has a FPGA on the head that implements the HPU core that allows to collect events from the other neuromorphic sensors. So we took advantage of this FPGA to integrate our FPGA, our cochlear model. So we connect the microphones of the iCub directly to the neuromorphic auditory complex, and the output of the neuromorphic auditory complex was connected directly to the HPU core. The output events from the HPU core were sent to the computer, and this computer sent events to Spinnaker platform. And the features or the configuration that we integrated on iCub was a NAS with right and left cochlea with 32 frequency channels, taking as input the I2S microphones and having as output the AER protocol. And for the Jeffers model, we use 4 networks connected to the channels 13 to 16 of the cochlea, with 16 coincident detector neurons having a maximum interval time difference detection of 700 microseconds with 10 microseconds of overlapping. Until this point, we didn't integrate it yet, the lateral superior olive, because it's still under development, but we will do in the future. And about the resources consumption, the entire design needed 83% of the resources, and the neuromorphic auditory complex needed half of the resources, 52%, having only the 15% of the resources of the FPGA free for the lateral superior olive model. In the software part, we for being able to read out the events from this new module, we needed to create a new type of event called ear, and we also needed to create a new decoding process to extract the frequency channel and the neuron identification from the package. Also, for making the demonstrator, we created some new visualizers that will help the researchers to do the task. In the Spinnaker part, we implemented 2 big networks, one network for the sound recognition and another network for the sound source localization. At the end, the idea is to combine the output of those 2 networks for doing some attentional models, but that's part of the future work. So next, I'm gonna show some preliminary results. And the first one is a plot of recording when a person is talking in front of the iCub, a set of keywords or speech comments. As we can see on the sonogram, we see that the power of the signal, and then we also see in the background some noise. That noise was produced by the iCub fans, because the iCub has 3 fans close to the microphones that is adding noise to the signal. In the right plot, we can see the average activity, which is the average number of spikes produced by the cochlea. And we can see that for each different word, we have different output from the cochlea. But as we can see that we have like a ground activity around 500. That's the noise produced by the fans. Then, to check the first check that we wanted to do about the Jeffers model, we started to move the iCub head in a loop from left to right while playing a 500 Hertz pure tone in front of the iCub. So in the left plot, we can see the output response of the cochlea, seeing that when the iCub is looking at its right, the left ear is closer to the speaker, so the level of the intensity of the sound is higher in the left cochlea compared to the right one. But as soon as the iCub start moving to look at the left, now the right cochlea has more activity. Then, for checking the Jeffers model, we plotted the output events from the medial superior olive model, and we clearly see how the model is able to extract this interaural time difference on the left plot, which is the raster plot, and also in the right plot, which is the first estimation of the sound source localization, just integrating the output events of the Jeffers model across time. Then we wanted to validate the model to check how the model behaves with low frequencies and high frequencies, because the Jeffers model, or the interaural time difference extraction, works better for low frequencies. So what we did was to place sound in the very right, 90 degrees on the right, and then we played a 500 Hertz pure tone and a 1.5 kilohertz tone. The left plot corresponds to the low frequency sound, and the right plot corresponds to the high frequency sound. And we clearly see how the model responds good to the low frequency, localizing good sound source. But when the input sound is high frequency, the model is not working because of the ambiguity. Then we wanted to check how the model reacts with the distance, because we know that when the sound source is far from you, you are not able to precisely localize the sound source. So what it did was to place the sound source close to the iCub and far from the iCub. So on the left, we can see how the response is better, or is located around neuron 5, when the sound is half a meter away from the iCub, but when the sound source is 3 meters away from the iCub, the response is more sparse between the neurons 4 and 7. So we can say that the model is working according to biology. Then we used the sweep movement of the iCub as input of the spinnaker of the inferior colliculus network on spinnaker to combine the output of the 4 networks and to have a final decision about the sound source localization, which is shown in the bottom plot. So we can see how the inferior colliculus network is able to say more or less where the sound source is. Finally, we wanted to do a live demo to take this spinnaker output to move the iCub head in simulation. So you can here see first on the top right the visualizers that we created to show the prediction of the iCub, and then the iCub in this case was moving from its left to the middle because the prediction said the sound source is in the middle. Some results that we extracted from this work was that the localization accuracy theoretically is the full range divided by the number of neurons, but in reality, it really depends on the distance in which you place the sound source. Then we thought that the maximum interval time difference that we are able to detect was 700 microseconds, which is the same as the humans, but in case of the iCub was 400 microseconds because the distance between ears is lower than the humans. And for the sound recognition accuracy that we tried with the pure tones was less than 65% due to the iCub's fan noise because it was adding too much noise. So the system that we already trained for another work was not working good. So some improvement that we will need to do in the future is to make our auditory models adaptive. And this means that we will need to adapt the model's parameters according to the input sound, so we will have a better response. And we will also need to improve our spiking neural networks to make them more robust to the noise and to have a more clear or precisely output. Then we would like to remove the iCub fan noise, either to replacing the fans or to doing some algorithm to attenuate the fans. And we would like to improve the iCub movement algorithm because until now it was so slow. And as future work, I would like to integrate our cochlea model with the other sensors to perform some audiovisual attention problems and to start working to the cocktail party problem. So I really would like to thank the whole group from Italy for their help with the first touch with the robot and with the software, and also to the project that funded this work. And also I would like to thank you for your attention.